It's not just about sending back error messages when things go wrong. It's about providing meaningful information so that clients can respond appropriately. In this lesson, we're going to cover how to effectively manage errors in your Spring Boot RESTful API, including defining custom exceptions, creating global exception handlers, and ensuring that your clients receive clear, actionable feedback. So far, we've learned about the essential components of building a RESTful API using Spring Boot, such as creating endpoints, implementing error handling, and configuring cores. We discussed the importance of structured JSON responses and how to use data transfer objects, or DTOs, to control the data exposed to clients. The significance of HTTP status codes, adding metadata, and versioning APIs were also highlighted to enhance usability. Lastly, we touched on testing API endpoints to ensure they function as expected. Now, we will dive into error management, discussing best practices to enhance your API's reliability. We'll begin by defining resource not found exception, which extends runtime exception, allowing us to effectively leverage exception handling within our Spring Boot application. The @response status HTTP not found annotation is absolutely crucial here. It instructs Spring to return an HTTP 404 status code whenever this exception is thrown. This means that any time a resource that a client is trying to access doesn't exist, our API can communicate this clearly with a standardized response. When creating the constructor, we'll pass in a message that can be used to provide additional context to the client. This customization allows us to enhance the error feedback, making it more informative. By using this custom exception, we improve our error management strategy, ensuring clients understand precisely what went wrong when they attempt to access a resource that's unavailable. This approach not only enhances usability, but also aligns with RESTful principles by providing meaningful and actionable feedback to API consumers. Here, the annotation maps the HTTP GET request for the specified path, allowing clients to retrieve a book by its unique identifier. As we define our method, we take a long ID parameter from the path, which represents the book's ID. To fetch the book from the database, we use the bookrepository.findID. We throw a resource not found exception. This custom exception provides clarity by including a descriptive message that incorporates the ID, allowing the client to understand precisely what went wrong. Once the book is retrieved successfully, we create a book DTO object with the book's ID, title, and author for a cleaner data transfer. Finally, we respond with an HTTP 200 status and the book's information encapsulated in the book DTO, ensuring that clients receive a clear and structured response when retrieving book data. Now, let's talk about implementing a global exception handler using the @controller advice annotation in our Spring Boot application. This technique will help us manage exceptions more effectively, ensuring that we can keep error handling centralized and avoid writing repetitive code in each controller. Within the Global Exception Handler class, we'll define two key methods for exception handling. The first one, Handle Resource Not Found Exception, is activated when a Resource Not Found exception is thrown. Here, we create a response map that captures the error message and then wrap it in a response entity with a 404 status code. This way, whenever a resource is not found, our clients will receive a clear and consistent error message. Now, the second method, called Handle Generic Exception, is designed to handle any unforeseen exceptions that might arise. It provides a generic error response by capturing all unhandled exceptions and sending back a 500 status code, signifying an internal server error. This setup ensures that clients have a uniform experience when they encounter issues, as they'll receive a well-structured JSON response no matter what type of error comes up. By implementing this global handler, we enhance the robustness of our API, ensuring that we communicate meaningful feedback to clients whenever errors occur. But wait, there's more to effective error management. You also need to provide meaningful HTTP status codes that accurately indicate the type of error you're dealing with. Think about the different client interactions you might encounter. These can lead to various issues. For instance, you might get a 400 for a bad request, a 401 for unauthorized access, or a 403 for forbidden access, and so forth. It's crucial that we differentiate these in our global exception handler. By doing this, you not only provide clearer feedback to users, but also make debugging easier for yourself and your team.
The horizontal bar chart, titled Frequency of HTTP Status Codes in Error Management, presents the observed counts for 6 status codes along the y-axis, with the x-axis labeled Number of Occurrences. Now, as we look from top to bottom, the chart lists these important status codes: 200 OK, 201 created, 204 no content, 400 bad request, 404 not found, and 500 internal server error. Next to each bar, you'll find the annotated counts. 200 OK has 150, 201 created shows 80, 204 no content at 30, 400 bad request at 60, 404 not found at 50, and finally 500 internal server error at just 20. The horizontal layout, along with the grid lines on the x-axis, makes it super easy to compare these frequencies. Now, if we focus on the data, successful responses like 200 and 201 really dominate the chart. On the flip side, we see client-side errors like 400 and 404 combining for a total of 110, which definitely warrants our attention. While server-side failures, represented by 500, are comparatively rare. Those labeled counts next to each bar confirm the exact magnitudes and will help support our prioritization decisions. So, it's clear. Our first focus should be on reducing client errors through better validation and clearer client guidance, especially with 400 and 404 responses. Next, we'll want to monitor and log those less frequent server errors to prevent any escalations. And let's not forget the prevalence of those successful responses. We can use that to fine-tune our alert thresholds and testing priorities. So, let's embrace this data. It's like a roadmap guiding us to improve our error management strategy.
Now, let's see how we can enhance our global exceptional handler to manage validation errors specifically. We begin by implementing a method that intercepts method argument not valid exception, which is thrown when a DTO fails validation, like when a user submits invalid data. Inside this method, we'll create a map to hold those error messages. This is where each field that failed validation gets paired with its corresponding error message. We achieve this by iterating over the field errors retrieved from the exception. So for each field error, we populate the errors map. This step is really important because it allows us to return detailed, user-friendly feedback to the client. Finally, we send this structured map back as a JSON response, along with an HTTP status of 400 bad request. This approach is crucial for effective error management because it empowers clients to understand exactly what went wrong and how they can fix their input before making another request. By providing meaningful validation feedback, we really improve the overall user experience and ensure our API is more robust and easier to use.
Now, let's implement error logging into our global exception handler. This class is crucial for centralizing how we handle exceptions across all the controllers in our application. So, first things first, we'll need to import the SLF4J logger and logger factory, which will allow us to enable logging functionality. By defining a static final logger instance linked to the global exception handler, we're setting the stage to capture error messages whenever an exception occurs. Now, let's shift our focus to handling generic exceptions. When something unexpected happens, the handle generic exception method kicks in. It logs an error message, including the details of the exception, which is super helpful for troubleshooting and monitoring the health of our application. By including the exception message in the log, we gain visibility into what went wrong, making our future debugging efforts a whole lot easier. So, in summary, integrating logging into our global exception handler not only empowers us to maintain a high level of awareness regarding application errors, but also leaves behind a trail of logs. This trail can tremendously help us trace issues, understand how clients interact with our system, and ultimately improve the reliability and performance of our application. Remember, this practice is fundamental for maintaining robust APIs in production environments.
We begin by defining a class called API error, which will encapsulate essential information about the error, like a descriptive message, the HTTP status code, and a timestamp to indicate when the error occurred. The constructor takes in a message and a status, setting the corresponding fields and initializing the timestamp with the current system time. All right, next we're going to modify our existing global exception handler, to utilize this uniform structure for our error responses. For example, when handling a resource not found exception, we create an instance of API error, passing in the specific exception message and the HTTP status code for not found. This way, when a resource isn't found, the response will be structured in a manner that API clients can easily parse. By returning an API error instance within a response entity, we ensure consistency across our error responses, making them not only more predictable, but also easier for API consumers to handle programmatically. This consistency truly enhances the overall user experience.
Now, let's dive into how we can implement a test to verify the error handling in our getBookById method, especially when a requested book doesn't exist. So, to kick things off, we're going to use Mockito to mock our book repository. We'll specifically configure it to return an empty optional when we search for a book with an ID of 99. This effectively simulates the situation where the book is not found in the database, which is a common scenario, right? Next, we'll utilize mockmvc to perform an HTTP GET request to the API/books/99 endpoint. After we've made that request, we can assert that the response status we expect is 404, indicating that the book wasn't found. But that's not all. We should also check the JSON response body to ensure it contains the correct message, confirming that no book was found with the given ID. This really aligns perfectly with our structured error responses, allowing the client to understand precisely what happened. By implementing this test, we're ensuring that our API's error handling functionality behaves just as we intend, which ultimately contributes not only to the reliability of the application, but also enhances the user experience when errors arise. As we wrap up our discussion on managing errors in a RESTful API, it's crucial to remember that good error management practices really enhance both the developer and user experience. Providing meaningful errors not only helps users interact with your API more effectively, but it also gives valuable insights into what might be going wrong during those development and maintenance stages. Now, implementing custom exceptions, along with a global exception handler, meaningful HTTP status codes, effective error logging, and standardized error responses creates a robust error handling mechanism. This setup lets developers focus on building features instead of constantly troubleshooting. So, next time you're building a RESTful API, keep these best practices in mind. With them, you can construct a more resilient and user-friendly API that thrives, even in the face of errors. Happy coding, and see you in the next lesson.